On April 13th, 2026, a major technical presentation introduced a controversial metric. Industry specialists had spent decades classifying this exact achievement as fundamentally unattainable. The specific figure projected onto the conference screen was 48.41%. To accurately grasp the significance of this thermal metric, we must evaluate standard energy dynamics. When petroleum fuel undergoes rapid combustion, the vast majority of the generated thermal energy simply dissipates. Standard consumer vehicles convert merely 30% of the available combustible energy into forward mechanical motion. The remaining 70% dissipates entirely as wasted exhaust heat and internal mechanical friction. This massive energy loss provides absolutely no propulsive value to the overall transportation system. For more than a century, global automotive engineers have systematically attempted to minimize this thermal dissipation. The previous historical peak for mass-produced internal combustion efficiency stood at exactly 41%. That specific industrial achievement required billions in continuous research and development funding. Prominent manufacturers established this numerical threshold as the definitive engineering ceiling for the entire market. They argued that surpassing this limit would violate fundamental physical boundaries and prove financially unviable. However, the newly recorded thermal metric completely dismantles this deeply established corporate paradigm. It demonstrates that the rigid 40% limitation was largely a financial barrier rather than a strictly physical constraint. Following independent verification, this specific efficiency rating of 48.41% was formally registered as an official Guinness World Record. That historical 40% barrier was directly dictated by the fundamental laws of thermodynamics. Every internal combustion system operates within a rigid physical boundary known as the Carnot limit. The process starts when atomized fuel ignites under high pressure inside the chamber. This ignition triggers a rapid expansion of gases. The expanding force drives the heavy steel piston downward, initiating the mechanical motion intended for the wheels. However, this sequence generates intense thermal energy. Combustion temperatures spike well beyond 2000 degrees Celsius. This peak heat is 3 times higher than the melting point of standard aluminum engine blocks, which sits near 660 degrees. Heat behaves according to its own rules. It ignores the drivetrain. The thermal energy instantly penetrates the cooler metal walls of the cylinder. It radiates through the cast iron liners. It dissipates into the surrounding liquid cooling channels. A massive volume of the remaining thermal energy simply rushes out through the exhaust pipe before doing any useful work. The Carnot limit dictates the maximum theoretical efficiency based on the temperature gap between the initial explosion and the exiting exhaust. To extract more mechanical power, engineers must widen this thermal gap. Yet, this creates a severe engineering trap. Pushing the combustion temperature any higher directly increases the risk of melting the cylinders and destroying the entire engine block. To bypass the risk of destroying the engine block, Toyota engineers spent decades fighting thermal losses. The company invested billions of research dollars into a mechanical solution to cross the 40% threshold. They resurrected the Atkinson cycle, a concept that modifies standard valve timing. The intake valve remains open slightly longer during the compression stroke. This brief delay pushes a fraction of the air-fuel mixture back into the intake manifold. The engine expends less energy compressing the mixture before ignition. In 2017, Toyota released the 2.5-liter dynamic force engine. It achieved a verified thermal efficiency of 41%. Getting a combustion engine from 35 to 41% required years of expensive refinement. The industry viewed this figure as the final peak of traditional gasoline technology. Surpassing this metric without catastrophic cost increases seemed economically unviable. Instead of chasing another costly percentage point, the global automotive sector shifted its timeline. Major Western engineering groups halted internal combustion development. They redirected their massive budgets exclusively toward building battery electric platforms. While Western developers abandoned internal combustion entirely, Chinese engineers reimagined the hybrid architecture. Traditional platforms lose kinetic power on steep gradients and difficult terrain. Why does this mechanical drain happen so consistently? The combustion engine adjusts its revolutions continuously to follow the spinning wheels. It surges violently uphill. It drops rapidly at every urban intersection. Every single fluctuation pulls the system completely out of its peak thermal window. Build Your Dreams eliminated this persistent mechanical compromise. They disconnected the combustion block from the drivetrain completely. The heavy mechanical linkage disappeared entirely. The internal combustion unit became a pure onboard power station. How do you bypass the massive energy drain of traditional planetary transmissions? You lock the engine at one perfect operational speed indefinitely. The primary electric motor propels the heavy vehicle forward. It accelerates the car smoothly, smoothly from a dead stop directly to highway velocities. Meanwhile, the gasoline unit maintains a singular steady state. You hear a constant, monotonous hum beneath the heavy metal hood. The pistons cycle at precise, optimal revolutions, completely ignoring the rapidly changing road surface outside. This strict division of labor defines the Generation 5 DMI platform. The singular focus yielded unprecedented results in modern automotive thermodynamics. Engineers officially recorded 46.06% thermal efficiency. This absolute metric genuinely stunned the global automotive press. A 5% leap seems relatively modest at first glance, yet Toyota spent roughly 20 years chasing that exact mathematical margin. Japanese development teams invested massive billion-dollar budgets just to climb from 36 to 41%. The Chinese manufacturer achieved their monumental jump in a mere fraction of that time. They bypassed the friction of mechanical gearboxes completely. They simply stopped forcing the engine to chase the varying road speeds. The combustion hardware provides continuous electricity while the vehicle climbs steep mountain passes. Every injected drop of fuel converts directly into high-voltage electrical current. The battery pack balances the energy flow for the entire propulsion system. This radical architectural shift officially locked in 46.06% efficiency. While that particular architecture secured an official 46% rating, competing developers changed the fundamental injection geometry. The traditional internal combustion engine faces a deeply inherent fluid dynamics problem. When air and fuel enter a standard internal cylinder, they rarely combine into a perfectly uniform substance. This structural limitation creates an inconsistent distribution of combustible material. You end up with localized microscopic areas containing dense fuel, while adjacent zones hold mostly plain air. When the electrical spark ignites this uneven composition, the resulting flame propagates slowly across the space. It entirely fails to ignite the whole required volume simultaneously. During this sluggish wave of physical combustion, thermal energy bleeds outward into the surrounding metal walls. This continuous heat loss to the heavy engine block represents a major overriding physical barrier. It traditionally restricted standard thermal efficiency from progressing past recognized conventional limits. To overcome this thermodynamic limitation, mechanical engineers redesigned the physical structure of the air intake channels. They specifically modified their internal geometric shape and direct approach angles to manipulate the atmospheric flow. When the critical intake valve opens now, incoming atmospheric pressure does not drift passively inside. The strict geometric channel contouring actively forces the gas into a high-pressure rotating turbulent vortex. This extreme mechanical agitation creates an exceptionally homogeneous molecular mixture directly above the moving piston head. Once the electrical charge releases into this pressurized environment, the slow-spreading flame front disappears. Instead of a creeping thermal wave, the entire dense mixture detonates in a sudden localized explosion. The resulting aggressive combustion expands outward uniformly in all possible directions at once. This synchronized chemical reaction delivers a massive downward kinetic force directly onto the mechanical components. It pushes the piston downward before excess thermal energy escapes into the surrounding metal structure. The sheer speed of this simultaneous burn dramatically reduces thermal transfer waste across the block. It converts a higher percentage of the initial chemical reaction into usable direct kinetic force. However, this profound structural modification introduces a severe operational challenge inside the pressure chamber. Forcing such a pressurized turbulent fuel mixture to detonate instantaneously fundamentally alters the cylinder environment. This aggressive approach to volumetric combustion drastically elevates the underlying risk of dangerous premature detonation. The immense pressure inside the combustion chamber creates a volatile thermal environment. It threatens to ignite the dense fuel mixture before the spark plug fires. Engineers faced a strict physical boundary for years. Extreme internal compression generates extreme heat. This concentrated thermal overload guarantees catastrophic mechanical failure. For over 2 decades, this exact thermal wall stopped mass-produced engines from breaking the 41% efficiency mark. Geely bypassed this barrier by manipulating the heat gradient across a single metal structure. They engineered a power plant operating hot and cold simultaneously. Standard automotive cooling systems pump a 50-50 ethylene glycol mixture through the entire engine block at a uniform rate. They maintain one single target temperature. This compromise treats the top and bottom of the cylinder as identical thermal zones. They are fundamentally different environments. components. Geely divided the internal fluid network into two isolated thermal circuits. The cylinder head sits directly above the explosion area. This upper zone demands rapid thermal reduction. Thermal sensors constantly monitor the aluminum surface. A dedicated electronic water pump alters the fluid pressure. Pressurized antifreeze immediately floods the upper cooling galleries. The system maintains the cylinder head at 90 degrees Celsius. Coolant flows rapidly through this high-stress section. It pulls heat away the exact millisecond the combustion occurs. A cold cylinder head keeps the incoming oxygen charge highly dense. The volatile fuel remains stable right up to the planned ignition point. This precise temperature control eliminates premature engine knock. It allows the hardware to run a massive compression ratio without self-destructing. Higher compression simply extracts more kinetic energy from every single injected fuel drop. Meanwhile, the lower engine block manages an entirely different thermal reality. The aluminum pistons slide inside these lower sleeves thousands of times per minute. Here, the control unit deliberately traps the generated heat. The lower block operates at a sustained 105 degrees Celsius. This stark temperature contrast serves a critical mechanical purpose. Heat alters internal fluid dynamics. The retained warmth physically thins out the synthetic engine oil. The physical shift is drastic. When the internal oil temperature rises from 80 to 100 degrees Celsius, its kinematic viscosity drops by nearly 50%. The thick lubricant becomes a thin, slippery film. The pistons glide through the heated cylinders with minimal surface resistance. Every fraction of eliminated mechanical friction translates directly into forward momentum. That energy reaches the drivetrain instead of radiating away as useless heat from metal scraping against metal. Traditional engine geometry forces a hard choice between a cold head for dense compression and a warm block for fluid lubrication. These two physical goals directly oppose each other. This dual circuit architecture forces both states to coexist just centimeters apart. The entire divided network relies on the primary electronic water pump. The main controller reads thermal sensor data dozens of times every single second. It instantly recalibrates the internal hydraulic pressure and independently adjusts the coolant flow across both isolated circuits in real time. Perfecting cylinder thermal balance means nothing if rotational force dissipates downstream. Transmitting torque through a multi-speed gearbox degrades efficiency. Traditional transmissions are dense blocks of aluminum and steel. They house heavy hydraulic torque converters, brass synchronizers, and compressed clutch packs. Pressurized transmission fluid circulates through the valve body to engage these components. Friction occurs constantly. Alternating steel plates and friction-lined discs rub together within the viscous fluid. This drag generates heat. The metallic assembly weighs over 100 kilograms. Even the electronic continuously variable transmission relies on interlocking sun and ring gears. That planetary concept debuted in the 1990s. It is over 25 years old. Today, those intermeshing metal teeth create unnecessary mechanical resistance. Up to 15% of the generated power is wasted inside the transmission casing before the tires touch the asphalt. To eliminate those persistent transmission losses, engineers completely replaced the 100 kilogram gear assembly with a single electromechanical module. They developed a comprehensive 11-in-1 intelligent drive system, removing the traditional gearbox entirely. Instead of utilizing shift forks, synchronizer rings, and hydraulic fluid channels, software algorithms now dictate the precise physical distribution of energy. The new powertrain architecture packages the internal combustion engine, the primary generator, twin electric motors, the high-voltage inverters, and the advanced thermal management hardware into one consolidated casing. Consolidating these critical components reduced the total weight of the aggregate by 13.5% compared to previous hybrid setups. For 90% of standard urban driving, the engine maintains zero physical connection to the drive wheels. The cylinders merely spin a generator at their peak efficiency threshold. From the driver's perspective, the interior experience remains completely seamless. It operates with the smooth acceleration of an electric motor, avoiding the subtle physical jerks typically associated with mechanical gear shifts. The internal control unit recalculates the most efficient energy distribution pathways 50 times every single second. This rapid processing speed allows the artificial intelligence to evaluate the active navigation route up to 3 kilometers ahead of the current position. The software analyzes the upcoming topographic topographical changes and makes continuous real-time adjustments based on satellite elevation data. When the sensors detect an approaching descent, the control module immediately shuts off the combustion engine to initiate a coasting phase. The vehicle relies entirely on gravity and regenerative braking hardware to maintain momentum while recharging the battery cells. Conversely, prolonged highway driving demands a different mechanical approach for optimal efficiency. Above 128 kilometers per hour, routing power through electrical conversion pathways becomes demonstrably less efficient than utilizing a traditional direct connection. The software instantly recognizes this high-speed threshold and mechanically locks the engine directly to the axles. This selective engagement provides a physical override, bypassing the electrical components entirely to maximize kinetic transfer. The structural integration of the 11-in-1 drive unit combined with the split thermal cooling zones and continuous artificial intelligence power routing yields highly optimized efficiency metrics. The vehicle achieves a certified consumption rate of 2.22 liters per 100 kilometers. This precise fuel consumption figure officially established a new Guinness World Record for production hybrid vehicles. Because the software manages every drop of hydrocarbon fuel and every electron passing through the inverters, the boundaries of hybrid transportation have expanded significantly. A fully fueled and charged vehicle operating under these exact parameters now delivers a combined driving range exceeding 2,000 kilometers. Achieving a 2,000-kilometer range without a scattered charging network rewrites the economics of heavy passenger transport. Across vast distances, pure electric platforms face strict physical realities. Moving a massive chassis requires immense energy storage. A standard electric vehicle battery pack weighs over 500 kilograms. That is half a ton of dead metal. Drivers haul this weight on every trip. Fast charging infrastructure remains sparse across large sections of the globe. Range anxiety creates a firm logistical barrier. This new hybrid architecture delivers different geographic mobility. Drivers utilize silent electric torque for urban commuting. The battery handles daily traffic, yet the vehicle crosses continents without waiting for grid connections. You refuel at any standard petrol station. Combined fuel consumption drops below 2.5 liters per 100 kilometers. This is not a lightweight compact car. It is a heavy sport utility vehicle maximizing every drop of fuel. For traditional automakers, this geographic shift exposes a deep engineering deficit. The internal combustion engine was born in Europe. Germany, France, and Britain dominated this hardware for over 100 years. They controlled the market. Then the manufacturing center moved east. Japan spent 50 years refining the mechanical architecture. They pushed thermal limits towards strict physical boundaries. Now the timeline collapses. The worldwide combustion efficiency record belongs to a completely new competitor. This brand lacked any serious global automotive presence just 15 years ago. Closing this technological gap requires massive structural changes. European and Japanese manufacturers cannot rely on simple firmware updates. Software cannot mask mechanical disadvantages. They must rebuild entire engineering pipelines from the ground up. This demands years of dedicated laboratory research to match these exact numbers. Meanwhile, strict financial realities restrict their strategic movements. Shareholders demand heavy capital allocation for new electric platforms. Legacy automakers face intense investor pressure, while their core gasoline technology rapidly loses market competitiveness. The technology gap between legacy European conglomerates and new hybrid platforms requires a complete overhaul of established engineering roadmaps. For decades, traditional manufacturers viewed the 40% thermal threshold as a final physical barrier. However, history reveals that this boundary was strictly financial, rather than a fundamental law of thermodynamics. Legacy companies simply stopped funding research. Now they must react. 48% thermal efficiency establishes a new global benchmark for internal combustion architecture. 48.41% is now an officially recognized record, achieved in a technology that major corporations confidently dismissed as a dead end.